know already. So binary search trees. I guess you guys have been taking binary search trees. And so binary search trees implement the sorted set interface. And that is, they do find x, add x, remove x. So yeah, if you guys have trouble hearing me or if I'm going too fast or too slow, just let me know. All right. All right, so binary search trees. Now, let's see here. So these are binary search trees. And they do find, add, remove, and these are basically, yes? Yeah. Hello?
Can you turn up the volume?
All right, maybe. Is this better? Slightly better? I'll try and talk louder. Okay, so a binary search tree, we do, so all these operations, find, add, or remove, basically walk down the tree. So they're going to take time, what? Log n, ideally yes, but more specifically, it's going to be the height of the tree, right? So these are not necessarily balanced. These are just binary search trees. And because they're just binary search trees, it could be that they're not balanced and they're just basically a list, right? Pat probably went over if on certain inputs how you can get a tree that just looks like this. And then anything you want to find is basically O of n. So then from there you went with, he showed you random binary search trees. And then he showed you treeps. So treeps have all the nice properties of random binary search trees except they're dynamic. So a random binary search tree, you just sort of shuffle up your input and then you build your tree, and with high probability it will be a balanced tree. So then you can get your height will be log n. So treeps have that property except that they're dynamic, so you can do remove and add operations in expected log n time. So that's great. That's a nice property of binary search trees when they're balanced, is that you get log n time on all these operations. Of course, this is randomized. So what we're going to look at today is a deterministic binary search tree, balanced binary search tree. So what that means is that we can guarantee that the height will never exceed some asymptotic of log n. So what we're going to look at is a tree named after the idea that if you lose the election, that you can always find someone to blame. So it's a scapegoat tree. So in it, what we're going to do is if the tree ever gets unbalanced, we're going to look for some node that we can blame, and then that node is responsible to rebalance the tree. And all right, so let's define this. So this is going to So it will implement the sorted set interface as well. Ideally, you would probably just want to, if you were implementing it, you would just want to subclass binary search tree and then sort of modify your methods. But right, so what we're going to do for a scapegoat tree is we're going to have a value n that we keep track of, and this is the number of nodes in the tree. We're going to have a value q that we keep track of. Now q is just going to sort of make sure that the tree never gets too big or too small, and it is going to be at least n and at most 2n. And then the only other thing that makes it a scapegoat tree is that the height is at most log 3/2 of q. So log of 1.5 of q. And so if you remember about logarithms, the base is basically, so the value of log 3/2 of q is basically the number of times you can divide q by 3/2 until you're down to 1 or less. So this value here, because q is at most 2n, this is at most log 3/2 of 2n, which is equal to log 3/2 of n plus log 3/2 of 2. So basically the height's going to be log n plus this very small constant that's less than 2. So basically it's going to be O of log n. Okay. Okay. So it's all fine to have all these nice properties. If we can maintain all this, then scapegoat trees would be something that's nice to use. So we have here, we have O log n Now, what I'm not showing here, so the find, add, and remove are all going to be O log n, but there's going to be a little bit of rebuilding going on here. So we're going to show exactly how much extra work we have to do. But first, we have the definition. So now we want to show how we implement find, add, and remove, and still maintain these properties. So find is, you find your node. Nothing changes. You don't increment n. You don't change q, and the height doesn't change. So nothing changes on find. We can just call the superclass find and on the binary search tree, and that will work. All right. So we'll do remove, since this is the easier case. So to remove something from a scapegoat tree, we do the following. So we call super.removeX. Or if you're not implementing it as a subclass of the binary search tree, you do the same thing. You guys know how to remove from a binary search tree, yeah? So you step if we want to remove our root here, let's say if we want to remove 4, then we step right and then go left as far as we can. So we find 5, and we delete 5, and we use that to replace 4. So that's the remove, and that's what we do here. So the next thing that we want to do is we want to decrement n, because we now have less nodes. You guys do your code in Java, or? Yeah? Okay. So this is sort of pseudo Java. Right, now, so we've decremented n now. Is this still a scapegoat tree? So what may be changed? I'm sorry? Okay. I think it's different. I'm not sure what he did last class. He said he did up to treeps and random binary search trees. Yeah, that's probably the treep. So that's where it's priority. It's you add things, but there's also a priority number that you generate randomly.
Yeah, but it has a way of like storing.
Yeah, and then it restructures based on that, and so that it looks exactly like a random binary search tree if you added these nodes in the order according to priority.
Okay, so what's the difference with the scapegoat?
The scapegoat tree, so that is a random tree, so it runs in expected log time. This is a deterministic, so it's going to run guaranteed log time. And the other difference is, well, you'll see the. Yeah. And by run, I mean the height will be some log factor. Okay. Right. So if we decrement n, then it could be now that, yes? Super what? Yeah, sure. Can you see these numbers, or should I make them? Yeah? I'll make them bigger anyway. So this is, let's see. And this could be any subtree, or it could be a tree all on its own. So we want to remove 4. And what we do is we find 4. And once we've done that, we've come down here. Then we want to find a replacement for 4. So what we want is the number that's closest to 4. That's either the least value that's greater than 4, or the greatest value that's less than 4. So either way, if we put all these numbers in sorted order on a line, and we remove 4, then we want to replace it with either 3 or 5, basically. And so to find 3 or 5, we go from 4. Assuming that we're going to go for 5, we go right, and then we go as far left as we can. So in this case, it's only once, but I mean, well, I mean, I don't have any room if we're using integers, but you know, technically, you can go all the way down and to some value down here. So let's say, because we've gone as far left as we can, we know that 5 has no left child. It only has a right child. So we want to delete 5, and we want to replace 4 with 5. So we do that. And then this child, let's call it 5.5. I don't think there's any real difference. You can even flip a coin, really. That's, I mean, you know, it might be some application-dependent scenarios, but for the most part, it doesn't matter. But if you choose randomly, then maybe you might end up with something more balanced if you have some set of input that's very regular. Okay, so remove n minus n, yeah. So we've decremented n, and now it could be that q is greater than 2n. So by our definition, this may not be a scapegoat tree anymore. So what we do in this case is we just rebuild the whole tree. So for the code, we check if q is greater than 2n, then we rebuild, we'll call it t. And by rebuild, what we're going to do is we're going to build it into a complete binary search tree, which means it will be balanced. And how we do that is we can do, well, this is already balanced. Let's So if we were going to rebuild this tree rooted at 2, then you can do an in-order traversal, right? So that then you read all the elements and you output them in sorted order. So you can read them into an array. 1, 2. And then you're going to take the median element, so the element that's closest to the middle. In this case, we'll take 3. That's your root. And then you recurse on the right and left side. So you take the median element of 1 and 2. Let's say that's 1. And then, so you're left with 2, which goes down here. And on the other side, your median element is 5. And then 4 and 6. So we've taken this sort of scraggly tree and we've rebuilt something that's balanced. Now, the left side and the right side are going to differ by almost 1 node. And so it's not going to be complete in the sense, like normally if you build a complete tree, it's going to look, you build it left to right or something. So you add nodes along here. But in this case, you could have it look like this or whatever. But it will be balanced. And it will be, the height will be minimal height. You can't build a tree with that number of nodes that's any less. You can't build a binary search tree with that number of nodes that's with a height any less than that. So then once we do that, we set q equal to n. And that's it. That's our remove operation. So now we have so our q is equal to n, which is fine. N number of nodes is fine. Height, well, the height is minimal now. And I mean, if you want to get more specific, this height is floor of log 2 of n, and that will be at most log of 3/2 of n, which is because 3/2 will divide into n at least as many times as 2 divides into n. So then we've satisfied this other condition that our height is at most log 3/2 of q. Okay, so that's remove. So we can do a remove. Now, like I said, so find, we don't have any extra. But for remove, we have the O log n usually, but sometimes we have to rebuild the tree. So I'll show you later how to do that. For now, we will move on to add. 26. Okay. So add x. So again, for the code, we do super.addx. And then we increment n, because we have an additional node in the tree. And we also increment q. Now what can go wrong? So we've incremented n and incremented q. So n is fine. Q, if it was less than 2n before, it's going to be less than 2n now. And if it was greater than n before, it's going to be greater than n now. But the height, well, the height might not work. So we're going to go through an example here. This, can you see that? Yeah? All right. Okay. So this is a scapegoat tree with, let me see here, 5. Did I forget one? Oh, yeah. So we have 9 nodes. We're going to say that q is also equal to 9. So we haven't deleted anything yet. And log 3 halves of 9 is 5 point something. And we're going to call add 6. So first thing that it does is it will add the node according to how we normally add in a binary search tree. So we start at the root. 6 is less than 10, so we go left. It's greater than 2, so we go right. It's less than 8, so we go left. Greater than 4, we go right. Less than 7, we go left, and greater than 5. There's nobody there, so we add it in. I'm going to cheat a little here. 6. And then we increment n and increment q. And now, so our height before was 1, 2, 3, 4, 5. So height is equal to 5. And now we've added a node, so it's become 6. And log 3 halves of 10 is equal to, again, 5 and change. So these logs are really slow growing. So when you increment the n by 1, then this value doesn't always increase by an integer value. So now we have a problem because our height is greater than log 3 halves of n, or log 3 halves of q. So we don't have a scapegoat tree anymore. So now here's where we find the scapegoat. So what do we do when we have a problem? Is we rebuild, yeah, but we don't want to rebuild the whole tree in this case. We want to find someone to blame, really, the scapegoat. So who are we going to blame? So this is the guy we added right here. So generally, who do you blame for your life not turning out the way it was supposed to? Your parents, right? So you go. So number 6 looks at his parents, which is 5, and says what we're looking for is a scapegoat. So the definition of scapegoat is a node W such that the size of, here, let me just readjust here. So our scapegoat is a node W such that as we go up the path back to the root, that the child that we encounter over the size of the child over the size of the W itself is greater than 2/3. What that means is this is W, and we've inserted X down here somewhere. Then this subtree rooted at the child of W is at least 2/3 of the entire size of W. So we have this really unbalanced tree. And so that makes W our scapegoat. So this unbalanced tree, if we rebuild it, we can make it nice and balanced and reduce the height of the tree. So how do we find this guy? Well, we just go up and keep comparing these sizes. So in this case, we start at 6. We look at our parent 5. So the size of 6 is 1. The size of 5 is 2. It gives us a ratio here of 1/2, which is less than 2/3. So that guy's okay. So next we go to 5. Our size is 2. The size of 7 is 3. Now that's exactly 2/3. So that's still okay because we want greater than 2/3. We go up to 4. Now the size of 4 is 1, 2, 3, 4, 5. The size of 7 is 3, so that's 3/5. Still less than 2/3. So we go up to 4 and look at 8. Size of 8 is 7, and the size of 4 is 5, which is 5/7, which I'm pretty sure is greater than 2/3. So that makes 8 in-order traversal. So that will give us, read all your elements into array, 3, 4, 5, 6, 7, 8, 9, and I'll give this for now. So now we take the median element, which is 6, and then recurse on the left and right side, so we get 4 over here. Five, and on the right side we get 8 as the median. You just read it into an array, so you know the size of the array. So then you can, so if the size is 5, the median is obviously 3. It's divided by 2, and then you have to do a little more arithmetic for the left-hand side and right-hand side, but still pretty straightforward. Right. So the in-order traversal takes linear time. and then linear time to build. So, right. So rebuild is, yeah, let's put that over here. Rebuild is linear in the size of the tree that we're rebuilding. So, is yeah, ish. O of the size of this. So if we're rebuilding the whole tree, it's O of n. But if we're rebuilding a subtree, then I'm sure it's O of n, but it's we can get a tighter bound than that. Yeah, because it's the size of the subtree, which not necessarily the whole tree. And we're going to actually show that it's using amortized analysis that it's linear in the number of nodes that you touch when you do all these operations. But I'll show you that in a minute. So we've rebuilt this, and because this is a minimally sized subtree here, right. So, yeah, so there's always going to be, because this is unbalanced, that there's going to be room to lift this node up. I could prove it more formally than that, but I'd rather not. So we do this, the height decreases by at least 1, which means that since our height can, if we add 1 node, our height can increase by at most 1. Then we rebuild, it decreases by at least 1, then our height will be within range again here. So again, we have a scapegoat tree. So we can do find, add, remove, and we can maintain all these properties on the scapegoat tree. So there's a couple questions left. So one, is there always going to be a scapegoat? Can we always find one? What's that?
Not if it's balanced.
Not if it's balanced, right. But then if it's balanced, will we ever have a case where the height is greater than log 3/2 of 2n at most? Or so log 3/2 is, of course, going to be something greater than log 2. So log 3/2 of n is greater than log 2 of n, or at least log 2 of n. So the height of this tree, if it's a balanced tree, it's log 2 of n. So it can never exceed log 3/2 of n. So if it's balanced, we will never have to rebuild our tree, basically. So we only rebuild it if it's unbalanced. And the claim is that if it's unbalanced, that we're always going to be able to find a scapegoat. So let's see. So let's assume that we can't find a scapegoat. So let's see what happens. So we've inserted this node, and then we run all the way up the tree to the root. And every one of these nodes that we look at, the child is never greater than 2/3 of the size of the child is never greater than 2/3 the size of the parent. So we always maintain this for every node W. Is less than or equal to 2/3. So that's true for everyone. So starting at the root, big old R, this is size n. So if we go all the way down to x, we've inserted. This guy is at most 2/3 of n, right? Now this guy is at most 2/3 of this guy, which means that he's at most 2/3 squared of n. This guy is again at most 2/3 of this guy. So that means he's at most 2/3 cubed of n, and all the way down to x, which we know is size 1. So, and x, if we've increased the height by adding x, that means the depth of x is equal to the height of the tree. So we go all the way down. This is at most 2/3 of the height times n. So, and the size of x is at most 1, which means that, so this is at most 1, which means that 2/3 to the height is at most 1 over n, because n over n gives us 1. So what does this tell us? What does that tell us about the height? Well, if we have let's just say it's equal for now. So if we inverse this, that means n is equal to 3/2. What did I do here? Right. 3/2 of h, and this is at most 3/2 log 3/2 of q. Right, and let's see. Right, right. The height is at most log 3. Yeah. So height is but we know that because we had to rebuild the tree that the height was actually greater than this, so that's a contradiction. Right, thank you. Sorry? All right. So yeah, so if we've added a node and it turns out that our height is greater than log 3/2 of q, then we know that we can find a scapegoat somewhere along this path from the node that we've added back up to the root. All right, so the other big question will probably be done a little bit early. But, so the other question is, how much does this rebuild operation take? So how much does the rebuild operation take? And the other thing that we're doing is as we're going up the scapegoat tree, we're calling size on all of these. So the other question is, how much time does it take to do these size operations? All right. So to do the size, we call size on each one of these nodes all the way up to the scapegoat. So we call add x, and so here we'll call x equal to u0, u1, up to uk, which is equal to our scapegoat, which we will call w. So these are all the nodes along this path from the node that we added up to the scapegoat w. And we call size on each one of these. And in each case, the size of u to the I over size of u to the I plus 1 is less than or equal to 2/3, except for u to the k. Oh, sorry. K minus 1, which is greater than 2/3. So then the price, I mean, if you're going to do this, you would probably just store the size at the nodes and save yourself a lot of time, but we'll go through this anyway because this is the way it's written up in the textbook. So all of these calls, we have, let's see. So we take a summation from, so again, if you recall, where did I show it? I think I erased it. But, yeah. So we'll go from k down to 0. Size of ui, and that is plus I equals k minus 1 to 0 size of ui, which is, so the size of the first child of w is at most the size of w, and then given that each one is at most 2/3 of the previous one, we get plus two-thirds I size of w. And then this is and then 1 plus two-thirds to the I, which is this is a geometric series, so it's a constant. I think it's 3 or something. So 1 plus, it's some constant times this. So all the calls to size are big O of size of the scapegoat. So when we rebuild, all the calls to size are still linear in the size of our subtree that we're rebuilding. Now the can erase all this. The other thing is, how much do these rebuild operations cost? So our claim is that if we start with an empty scapegoat tree, and we perform any sequence of M add or remove operations, which are the only ones that trigger rebuilding, that are all of our rebuilding is at most O of M log M. So that's the claim. So to prove that, we used amortized analysis. Which, have you guys seen amortized analysis? Yeah. All right. So we're going to use a credit scheme. So each time we call add or remove, we start with an empty tree, but then as we build it, so as we add a node, if we add, let's see. So if we add 4, it's less than 5, so we go here. It's greater than 2, we go here, and it's greater than 3, so we add it here. And then we add a credit for each one of these nodes that we've touched. And we store these credits at the nodes. So then the claim is that when you call rebuild, say if you call rebuild on 2 here, that there's enough credits there to pay for the rebuild operation. So we touch at most log M nodes over M insertions. So that's M log M. For deletions, it's the same thing. We add a credit for every node that we touch. But then after we delete the node, if we delete 4, we add another credit on the side. So on the side here, we basically have credits equal to the number of nodes that we've deleted or removed. All right, so the remove one is simple. So when we do a remove, we decrement N, but we don't decrement Q. So as we add nodes to our tree, Q is the same value as N, and then the difference between N and Q is basically the number of deletions that we've made. So once N is twice the size of Q, or more than twice the size of Q, that means we've deleted at least as many nodes as are left in the tree. So so if Q, right, so Q is equal to, Q is greater than 2n in this case, and then so it means we've deleted at least n nodes along the way, so we have enough nodes to pay for a rebuilding of the entire tree. So that's fine. So each one of these credits is not, it can pay for a constant amount of work. So some constant C, so we want to show that we have credits that are within a constant of the size of these subtrees that we're going to build. So if we have some subtree and the scapegoat is W, well, the last time that we rebuilt the tree, or when we added W, the size of W's left and right child are within one of each other. Because if we rebuilt it, we've chosen the median as W, so that means the size of the left child, the size of the right child differ by at most 1. So left child minus size is at most 1 after a rebuild, or if we've just added W for the first time, which means it has no children. So then we do a bunch of add or remove operations on W, and eventually we get to a point where we add, so we add some children here, always in sort of a balanced fashion. But then at some point, since W is the scapegoat, we know that this side got very large. And then we eventually added X, which triggered a rebuild because the tree was too high. So the number of nodes that we added is at least the difference in the size of these two sides minus 1, right? Because if we added 4 here, and this is at least 2/3 of the entire tree, then this part here is at most 1/3. In fact, it's less than 1/3 because this is greater than 2/3. So that means the size of the right child minus the size of the left child here is going to be, well, I did it backwards, but that's all right. Is at least 1/3 size of W. Because this is at least 2/3 the size of W, and this is at most 1/3. So that means as we've added and removed all these nodes, we've accumulated enough credits equal to 1/3 the size of W. So that's a constant fraction of the size of W, so we have enough credits to rebuild that subtree. And any questions or? And that's basically all I have for today. I figured I was going to go through this pretty quick, but so Pat will be back for your next class, next 2 classes, and then I will teach the Friday after that. I'll try and go a little bit slower, and then, yeah.